Hey folks, welcome. Azure Cosmos DB Live TV. I'm Mark Brown, and episode 54, we're going to talk about data modeling and partitioning with our friend Lenni Lobel. How are you, sir?
I'm well, thank you. How are you doing?
I'm doing great. I love your shirt.
Oh yeah.
Yeah,
Go
you know,
for
I played in a Pink Floyd cover band when I was in high school.
Oh,
So I have a
what
very
instrument?
I played bass.
Sweet.
So, but I played drums and I played some keyboard as well. I actually grew up playing church organ in a Catholic church where I grew up. So I have a strange musical background. But, oh no, I lost Lenni here. Hold on, Lenni? Where did you go? Oh no, there we go. Lost you for a second. I'm guessing my parochial school day story was scaring you away. I suppose.
No, not at all. Not at all.
So, my favorite topic in the whole world, data modeling and partitioning. I give this talk, or I talk about it a lot. And I'll tell you what, this is such a critical area for people to understand if they are going to use Cosmos, and not just use it, but also be successful. Like these concepts will help you learn how to design to scale, which is the whole point of having a database like this. But also more than just being able to scale, but also be efficient as well. So I'm really excited. I know our viewers are as well. So I'll let you go, and just know I'm gonna butt in with some comments and
Just shout
questions
it
along
out
the
at
way.
any time.
Yeah.
But let me just start off again by saying it's really a pleasure to be here. Thanks for having me again. And it is a critical topic, and I also talk about it a lot. And it is a bit of a mouthful, data modeling and partitioning patterns. Well, because to be successful at data modeling, you need to understand those partitioning patterns, and that's why it's that all in the title there. They go together. Our focus is data modeling, but we are going to need a fundamental understanding of how partitioning works in order to make sure that our data model is optimal, right? Ideally, efficient and optimal, right?
Yep.
You don't need to know about me too much. I've been around for a while. I'm in data platform MVP now for 11 years, and those books on the right, those are the older publications. My newer content is available on Pluralsight, including this topic. I do have a Pluralsight course that covers this very topic in more than, let's say, just an hour. So if you like what you see here, you can definitely check out my Pluralsight courses. I've also got related Cosmos courses on microservices, event-driven architectures, and just learning Cosmos DB.
I just want to say something, Lenni. I think your Pluralsight course on the intro for Cosmos, I think, is the seminal learning resource for people that are new and want to go from zero to hero using Cosmos DB. You do an amazing job, and anytime I run into someone and they're new to it, I say you should go and sign up for Pluralsight and take this course, because it's literally going to get you started faster and better than any other single piece of learning content out there. So
it's great to hear. I mean, I obviously love to hear that. Thank you so much for that. But of course, I really got to, at that point, shout out to your team, notably Andrew Liu, amongst others, but him chiefly. That really helped shape the structure of the course and make it a success. So really was a team effort there. Cool. So with that, I'm just going to jump right in to today's objectives. I'm going to assume that by now, maybe some of you are at least familiar with Cosmos DB, but maybe not all of you. And I'm certainly not going to make any assumptions regarding this session. And I'll make sure that we'll cover at least the most core concept in Cosmos DB and learn our best practices for data modeling from those concepts, right? Namely partitioning, right? Those core concepts I'm talking about is partitioning. And then based on that understanding of how that works fundamentally within Cosmos DB, how to best design a data model. And I'm talking now about a relational data model, because there's many different ways that you can model your data, right? But we're talking now about a relational data model, things that are very familiar and real world to us, things like Adventureworks type of databases that we've worked with over the many decades by now. And, we want to be able to make sure that we can understand the differences between that world and this very different world of NoSQL and Cosmos DB, this non-relational world. So again, I'm assuming that some of you, but not all of you, know a bit about Cosmos DB, and we're not going to cover, this is a loaded question. What is Cosmos DB is a loaded question. So we'll just focus in on two definitions, which are that it is horizontally scalable and non-relational, because it's many other things too. It's globally distributed, multi-model, it's schema-free, it has transactional capabilities, it has multiple APIs, can do lots of things. But for the purposes of this session, we are going to focus in on these two key characteristics, which are that it is what is often defined as NoSQL, horizontally scalable and non-relational. So what do we mean by horizontally scalable is that we have this logical container that to us looks like a single logical resource, but behind which, of course, there is a physical cluster of, let's say, servers, if you will, although the more accurate term would be physical partitions. But for this purpose, you can just think of them as servers, as actual boxes, each with their own CPU and disk storage, right? No different than a regular box. Whereas in fact, the term physical partition is more accurate, because each of these black boxes is more than just a physical box. It's actually a unit of replication. So even within a single data center, each of these physical partitions, each of these black boxes is replicated at least 4 times for failover and consistency, so that there's always a quorum. Even if one goes down, there's still 3 that can out of which 2 can satisfy a quorum. So, but that technical detail aside, let's just think of each of these physical partitions as just machines, servers, right? Each with its own CPU, its own disk storage, with no real upper limit to the number of these physical partitions that can participate in the cluster. And therefore, theoretically, at least, if we partition our data properly, we ought to be able to achieve both unlimited storage and unlimited throughput, right? Because we get more throughput and more storage with each additional physical partition added.
That's right. Each one has its own CPU with its own memory and IOP.
It's just like adding another box, right?
Yep.
Right, yep. Exactly. And just kind of but then of course that kind of hints away that you need to make sure you design things that allow you to take advantage of this, that allows the workload to be distributed across such a farm.
I mean, that's kind of the promise with being horizontally scalable, is theoretically you get infinite storage and infinite throughput, because you just add more. Theoretically, I mean, there's obviously practical considerations, like how many servers are in that data center or in that region, but theoretically, yes.
Well, but I mean, but you're going to hit an upper limit much sooner if you have an improperly designed data model.
Well, that's true.
Cosmos DB will be capable of scaling much more than you'll be able to take advantage. I said
it's the promise. You gotta follow the rules to get there, right? So yeah.
You just want to make sure that you scale infinitely, right? Unlimited storage, unlimited throughput, unlimited power. So let's drill down on those 2 terms: non-relational and horizontally scalable. Those are our 2 terms that we were drilling in on. So what do we love to do in the relational world with rows? What do we love to do more than anything? We love to join them, right? That's what gets us off, right? Having a perfectly normalized data model where you've got these beautiful parent child, primary and foreign key relationships, and your one-to-manys, and you're normalized. You're not duplicating data. You're joining as needed to get the relevant data, and to achieve an optimal non-relational. To achieve an optimal relational design. Well, in the Cosmos DB world, we don't store data in rows. We store data in documents, right? And there's certainly nothing you can store in a row that you can't store in a document. So there's nothing really stopping you from kind of designing things the same way. And what you might have stored in a row, you now store in a document. But otherwise, you do have these kind of pointers or references, if you will, parent, child, relationships between primary and foreign keys that you've embedded in these JSON documents. And while that is theoretically and technically possible, there's nothing stopping you from doing it, such a design breaks down. Such a design does not scale. Such a design is very expensive to implement, very, very costly, and take a lot of effort compared to doing things a little perhaps differently. Why is that? The answer is that ties back to our first term, it being non-relational. I'm sorry, being horizontally partitioned, because when you write a document to your container, it can land on any one of these physical partitions, and Cosmos DB will not enforce referential integrity in any way, nor will it actually join when it comes time to query these things together for you. So you have to fetch them yourself, and while you can certainly do that, that is not what Cosmos DB is designed, how Cosmos DB is designed to work.
One of the things I like to call out kind of about now is understanding a fundamental difference between relational and, say, a NoSQL database is consider the economic and technical environments in which each were born, right? So like relational databases came about in 1970. And consider at that time, in 1970, a megabyte of storage would have cost you between like $2,000 and $3,000. Like storage devices themselves weighed like a ton.
Storage is very expensive.
Very expensive. So if you wanted a gigabyte of storage, assuming you could even get it, because I guess you could if you added enough of those little disk drums or whatever, you're looking at about $2.5 million at today's dollars, right? Versus today, a gigabyte of storage in Cosmos is 25 cents, right?
Yeah,
so consider the economics of this thing are completely flipped than what they were, and why things like normalization and third normal form and fourth and fifth, whatever, were so important back then, because reducing storage actually was economically imperative to
and it had to fit in a scale up architecture.
That's correct, right? Versus today, when you look at like a NoSQL database, consider the environment they're born in. You have kind of a complete flip in terms of the economics of storage versus compute. But the challenge at the time for, say, like DoubleClick, what was the genesis of Mongo at the time, right? Their problem was dealing with gigabytes of data being ingested per second as part of kind of DoubleClick, which is kind of where a lot of that came about. Or say Facebook, where they're dealing with gigabytes of data being ingested, and they're trying to shard manually MySQL. I mean, that's where Cassandra was born, right? Another distributed database in there. So consider the challenges and what they were trying to solve for at the time these databases came about were fundamentally different, and I hope it helps to kind of illuminate why the databases themselves are designed differently and are optimized around different things. So
yeah, and because of all of these differences brought about by these change in economics and the world that we live in today compared to the world that those relational database engines, their heyday, it then will make you question whether it's even suitable for relational workloads. Since it's non-relational, there are no relational constraints, there are no joins. Is it suitable for relational workloads? And the answer, of course, is yes. Otherwise, I guess we'd be done now. Farewell.
Goodbye, folks.
We'd be done. And actually, that shouldn't say most workloads are actually relational. It should say many workloads. I don't know about most, because you can model your data in any way. You can model your data in an event-driven fashion, where it's inserts only or append only, where you are essentially logging events where the event itself could represent an update or a delete. And that's an event-driven architecture that can drive many microservices, but that is not what we're talking about here. We're talking about a relational workload for a stateful set of entities that we're storing in a database. And we certainly can do this. We just have to do things differently. We have to take a new approach to how we design our data model, and many of the best practices that are like embedded in our psyche at this point, they're embedded in our nature for having practiced them for so long. You go against those principles, you violate those principles because they like Mark was saying, part of that normal form development was in order to optimize on storage and now it's all about throughput, right? And data duplication is not as nearly the concern that it once was, although it is a concern in terms of now having to keep everything in sync. I mean, there is something to be said for a single instance of master data that you can join on versus denormalizing. But that aside, we have to have a real shift in the way we view the world of data modeling in order to be successful at implementing a relational data model in this non-relational world. And so what I've done is I've taken something that we're all super familiar with, presumably if you've been working with SQL Server at least for any length of time, you're familiar with the Adventureworks Database. At first, when I started this endeavor, I was going to refactor the entire Adventureworks database, but it turns out to be rather large. And then it occurred to me, I only need a handful of tables, let's say these 9, to effectively demonstrate, or let's say effectively represent the most common patterns that you find all over the place. Our one-to-ones, our one-to-manys, our manys-to-manys. So in terms of customers, we'll have a single customer table with 1 row per customer. Of course, our customer will have multiple addresses, which are stored in the related customer address table in a one-to-many fashion. Every customer has a password. And for whatever reason, and this is not necessarily for storage purposes, but just for normalization purposes, and the way that we update our data, we have chosen not to include the customer password information in the customer row, because we like to be able to update it independently, let's say, of the customer row. But it is still one-to-one. Every customer will have 1 password and any number of addresses. And then we'll have our products that we sell. So this is our web store model. This is, if you would imagine, an e-commerce scenario with a front-facing website where customers log in and browse your catalog and place their orders and manage their profile and things like that. That's kind of the scenario here. So, of course, you're going to have a product table, and those products are going to belong to a category in a one-to-many relationship between category and products, very typical. Products will also be assigned to tags, but we're going to have a many-to-many relationship there, which throws a small monkey wrench into things. At least in the relational world, the way we cope with that, of course, is with that inner table, that junction table there, that one that
table with just foreign keys.
Yeah, it's like right, pointing to one of each. You know what those are like. And then, of course, customers will have sales orders, and each sales order will have sales order details. So there's another one-to-many. There's and you've got actually one-to-many from customer to sales order details. So we've got multiple levels. We've got one-to-ones, one-to-manys. It's fairly representative. And if we can refactor this, then you can really refactor any such data model. But you can extrapolate how to do that, no matter how complex of your data model it is, assuming it is a properly designed, normalized data model, and you understand your most common access patterns. So when you are starting, when you're just starting with this, it is very common to think of a container as a table. And since you've got 9 tables here, you might think of creating 9 containers, right? And like you see them here, right? Because you would figure you would store your custom, all of the different types in tables of their own. And hopefully I've given you at least an idea up front that this would not be a good idea, that you could do this, but would it be a good design? No, it would not. It would not perform well for all the reasons we began explaining. Like, Cosmos is not going to join these things together for you. These things are scattered everywhere. You're going to have to retrieve everything yourself, and there'll be a lot of overhead. And it's not it's not how Cosmos was designed to work. Because Cosmos DB is a NoSQL database. So how are we going to do this? We're going to break it down. Let's start with the first level there, the customer level, the customer that has addresses and passwords. Let's break this down and refactor this. And it's always going to start with step 1, transforming these schemas into JSON, because Cosmos DB works with JSON. And that's exactly what I've done here. I've just transformed my column names from the tables into property names in JSON. Now, I've done 2 other things, one of which I had to rename the primary keys. So there's no customer ID here, it's just ID. There's no customer address ID here, it's just ID. Because in Cosmos DB, every document needs to have an ID property. It's the only rule on schema. Beyond that, you're free to design the schema how you like, but there needs to be a property called ID, and that is essentially the primary key along with the partition key, which we'll get to. But it helps identify each document. And the second thing I've done is I've camel cased everything, and that wasn't strictly necessary, but probably recommended. In the world of JSON, in this ecosystem, things are camel cased, so I've gone ahead and camel cased things as well.
The other thing you might want to do is convert your dates into ISO 8601 as well.
Sure. There's actually a lot more a lot more considerations like that. How you handle your dates, how you handle your booleans, how you handle your different data types. Yep. Those would be important considerations in the process here, because there's far fewer discrete types in JSON than there are in SQL for sure. And what you would have here is, you would still have a customer ID property here, which is your quote unquote foreign key. And I say quote unquote because there are no foreign keys. These are now references. So one document is referencing the other. So technically this works, but is this the way we want to go? Because this is JSON, we could also choose to embed that information, right? The addresses property could be embedded inside the customer as an array. I only have space to show one address, but you see it's an array. It could have, I won't say any number of addresses, but a good number of addresses in a reasonably sized overall JSON document. And the password object, which we decided to manage separately, is now embedded as well. And so which way to go, embed or reference, right? You can do it either way. So and the answer is you want to reference generally when you can. And when you can is when you have a one-to few or a one-to-one relationship.
You mean embed? Sorry. Yeah. Flip it. You mean embed? You want to embed when it's one to few.
What is that? What I'm sorry.
You said reference.
Sorry, you want to embed when it's one to few, whatever one to few means, versus a reference in general, right? If you can self-contain it, then it'll be better, as long as it's not, as long as it's reasonable to do so, which is the case with addresses, right? There's also a one-to-many relationship between customer and sales orders, but hopefully sales orders are unbounded, right? Hopefully you're going to have an infinite number of orders for your customers if you're going to run a successful business, and you're not even going to think of attempting to embed all the sales orders into the customer as well. That's not going to fit. We'll have to find another way of coping with that. But for the things that will fit, like addresses, it's totally reasonable to impose an upper limit of addresses. You could say 10 addresses, and that would be way more than you would ever need. And that would fit comfortably inside of a JSON document whose max size is 2 megabytes. So you will embed when it's one-to-one, like the password, or one-to-few, like it's the addresses. Or independent of that criteria, like even if you have something that's one-to-one, or one-to-few, you still might want to reference rather than embed if they're very rarely queried and updated together. Like they're just very different. They have very different usage patterns in terms of when they get queried or updated. In which case, the best candidate is certainly one-to-one, one-to-few, and they're queried or updated frequently together, because then it's a single query and a single update and not multiple, obviously. And then reference when it's one-to-many, right? When you have no choice, and you can't fit all the sales orders in one document. At some point, there's a boundary where it's not reasonable to embed anymore, and that boundary is when you approach that 2 megabyte limit on your document size, or you have any kind of unbounded relationship where you have to reference. And in that case, you can't embed. But as you'll see soon, if we partition things right, we can still kind of get our joins back that we're generally losing. But at least if you embed, if you think about it, you've gotten your joins back, right? At least at the customer level for its children and related entities.
Was that you who told me this once? Is relational databases do joins at runtime, and NoSQL databases materialize them to disk?
I don't think I said that.
I thought it was you.
Yours, but that's a nice way to put it. These are pre-materialized, right? The idea not having relational, of not having constraints, foreign key constraints, like orphan children that don't have parents. Well, that can never happen because the children are embedded within the parent. So you kind of get your referential integrity back in that sense. Plus, you also kind of, it's pre-joined, right? I mean, essentially, your child entities are pre-joined, solving the problem of not supporting joins. Right then and there. So that's what we're going to do. And you're not going to go with 3 documents. We're going to go with 1. And that's our first step toward improving our data model. As you'll see, we're going to go through 4 iterations of this. The first one is the bad one, the one where you have 9 containers. We're not even going to entertain that one. But this is version 2, let's say. We're going to improve that model with version 2 by embedding, first of all, here, the addresses and the password, and storing it in a container that we'll call customer, at which point we have to ask ourselves, well, how are we going to partition this container? And that's the critical, pivotal question for any container. How are you going to partition that container? It's partially, it's pivotal for so many reasons and critical for so many reasons, but one of them is that it's immutable. Like, you can't change it once you set it. And, among other reasons, it also is pivotal to the performance, and it's pivotal to the way you write your application. If you change the partition key, you also have to change the way your application interacts with the database, because you're often supplying that partition key with your individual operations, right? So invariably it's going to tie into your application logic if you change that partition key. So you want to get it right, and if you don't get it right, that's a separate problem. There are ways
what I tell people also in this, when they're early, because it's sometimes not possible to know everything. Like, I'm always surprised by how customers use my software, or have been. They often use it in different ways, and it's okay to iterate on designs, right? Especially if you're going through your dev and test. And
not only is it okay, it's inevitable that you will.
That's right. And then even in something like when you get to production, not uncommon for people to realize, oh, okay, I'm seeing different patterns here. I need to adapt.
It's a whole another discussion on that would be primarily focused on partitioning, rather than this session, which is primarily focused on data modeling. And we're going to now pivot to a discussion on partitioning, just so that we can get our data model optimal. But yes, there are things you can do to mitigate the pain of changing the partition key, but that's a separate conversation. Let's try to get it right the first time.
All right, next we'll do another show, folks.
Yeah, okay, and we can do another show on handling those scenarios. But now we're going to try to get it right the first time.
Okay,
that's the main thing. And in order to do that, we will pivot away from this exercise for a moment to our general discussion about partitioning, and then we'll come back around. So we know there's a cluster of these physical partitions behind each container. Let's just drill into 3 of them. And again, those JSON documents are going to land on any one of these physical partitions. And which physical partition they land on is not our concern. That is Cosmos DB is handling of physical partitions and adding new physical partitions when needed. That is not for us to concern ourselves with. What we need to concern ourselves with are what we call logical partitions. We determine a partition key that defines the logical partitions, where a logical partition will never span a physical partition. There's a caveat to that, actually. There's a new feature called hierarchical partitioning with it. There are subtle exceptions to that. But even in that case, at the finest level of granularity, okay, a logical partition will never span physical partitions, okay? So clearly, if you are selecting all the documents from a known logical partition, it's going to be much more efficient than when the known when the logical partition is not known, because then you have to check all the logical partitions, which of course means checking all of the physical partitions, which is what we would want to avoid generally for our vast majority use case. So when you create a container, you have to define that partition key. And I'm going to go with the username property, okay? I'm going to say that we have a username property, okay? And that is what we're partitioning on. And now the scenario is, for this exercise now, is a social networking scenario. Posts, comments, likes, things like that. User profiles. Imagine you're running your own Facebook, right, or LinkedIn type of platform, and you're going to choose the username as the partition key. What does that mean? That means well, first of all, forget about those physical partitions, right? It's actually better if you don't concern yourselves with them because Cosmos DB manages those. And let's just worry about the logical partitions. It will mean that every user's documents will be self-contained in their own logical partition. All of the documents in this partition belong to Tim and only Tim, even though these are documents of different types. So this could be a profile document for Tim. These next several could be some of Tim's posts. The next several can be a few of Tim's likes and so on, and maybe some comments. And all of these things, comments and likes, they're different schemas, they're different types altogether. But what they all share in common is that username property that all have the same value. Tim, or in the case of Andrew, these are all of Andrew's posts, comments, likes, etc. Right? And that's really the crux of it, because the schema has nothing to do with it. All right, it's just a logical organization of documents belonging to, in this case, a given user, because we've chosen the username property. It's important to know these physical constraints. I already called out the 2 megabyte constraint, so that's where that's what you're keeping in mind when you're considering embed versus reference, when you are determining, is this a one-to-few relationship? And what does few mean? Well, few means that you can comfortably fit what you need, and the document still doesn't exceed 2 megabytes. And if and when it does, and you need to store data in multiple documents, like customers and sales orders, for example, then you would want them in the same logical partition at least, right? And that will be nearly as efficient as embedding, because you're constraining it to the same logical partition, which has a nice healthy upper limit of 20 gigabytes. So those are your upper limits there. Partition splits is part of the magic in the way Cosmos DB works, because as you write to that container, these logical partitions grow. The physical documents get written to physical partitions inside these logical containers, and at some point, Cosmos DB is going to decide to split the partition. At what point? When a given partition becomes too busy. That could be too full, or it could be too busy on throughput for the throughput that you've provisioned. If you provisioned a high level of throughput, then Cosmos DB might need to split the physical partition sooner. Not might, will need to split a physical partition sooner than if you provision less throughput, right? Just to satisfy the SLA for the provided throughput, the provisioned throughput. And when that happens, Cosmos DB will take that physical partition and split it literally by spinning up a new physical partition and moving roughly half of the logical partitions off of the partition being split onto the new physical partition, and then continuing to proceed along the merry way. And that is really the beauty of Cosmos DB behind the scenes, managing the scale of your data as it grows and grows.
Hey, I got a question from a viewer here. Omar asks, what happens if you exceed the 20 gigabyte limit?
Yes. So you need to cope with that. You need to ask yourself why you're exceeding that 20 gigabyte limit. Is it? It's a little bit outside the scope of this conversation, but I do have a slide that shows this. I mean, there have been different ways to cope with this. One way is with synthetic partition keys, where let's say you've got device data where you would like to partition on the device ID, but there's so much data per device that it exceeds 20 gigabytes. You might have to qualify the device ID with the month, knowing that a month's worth of data for a given device won't exceed 20 gigabytes. But then, of course, you're forcing all devices to partition at the month level, even those devices that could fit all of their data in a 20 gigabyte partition. And for that, there's a new feature called Hierarchical Partitioning that lets you kind of do that, lets you exceed the 20 gigabyte barrier, where I'm going to actually defer that discussion. I'm going to defer continuing answering that question until I get to I think there's another slide that would be appropriate.
Hey, Omar, but if you do hit that limit, I think we throw a 409 back at you, and the container will not accept any more writes.
Yeah. It won't be met with a friendly
That's right.
response.
So this is why design matters here in understanding.
Right.
So.
So this isn't a nice looking picture, and maybe this logical partition here on the left is nearing 20 gigabytes, and will soon have that problem. But meanwhile, you look at many of the others, and it's so sparse. This is clearly not a good choice of partition key. This gives you what's called a hot partition from a storage perspective, at least. This is a much nicer looking picture. This looks like things are more uniformly spread across my container, or the partitions behind the container, much more uniformly. However, there could also be a concern on throughput, because if I partition on the date, for example, well, that will be a hot partition then on date, because presumably the application most of the writes are going to be for today. So if today is January 6th, all the writes are going to that middle partition. And the way you need to understand pricing is that when you pay for the throughput on a container, that throughput is divided evenly among all of the physical partitions of the container, however many physical partitions there may be. In this case, there are 3 physical partitions. If you imagine that I have provisioned and therefore I'm paying for 30,000 RUs per second, is a nice healthy number. It's a very high number. 30,000 RUs, I'm paying for that to get 30,000 RUs per second out of my container. Each of these physical partitions is getting 10,000 each.
Yep.
So you're paying for 30,000, you're getting 10 because of the design.
Yep.
Right. So that's a hot partition on throughput, and you want to certainly avoid that as well.
These partitions it's basically a share nothing architecture. These partitions don't know anything about each other. So there's no sharing or commingling of throughput or whatever. So yeah, it's funny you pick up date because that's I see that pattern quite frequently. We'll partition by that. It looks good from a storage perspective, because typically you'll have even storage, but from a request perspective, current is always hot.
Yeah, because all that's stale data and no one's querying it.
Yeah, the recency problem. Yeah,
right. That's why, again, going back to the username is a much smarter choice in this scenario for all the reasons we mentioned. It means that you can get all of Tim could get all of his documents, all of his posts, all of his likes, and so on, very efficiently. So what's a cross-partition query? A query that crosses logical partition, something that is generally undesirable, but not necessarily evil, and certainly not entirely avoidable. So don't even try to eliminate every single one of them. It's a matter of usage pattern. So if we have our documents partitioned by username, and we want to get all of Mark's documents where the username is known by the query, then we know exactly which logical partition, and therefore which physical partition we need to go route the query to in order to fetch the results without having to hit all of the others. And of course, if any sub-filtering within that logical partition, the same would be true, right? So I want to get all of Mark's documents, but within a given date range, or only of a certain type, like only the posts, or only the comments between this date range that belong to a given user. Those would all be single partition queries, satisfied by a single partition. Here is an equally innocent looking query, but the partition key is not known, and therefore obviously we want to find all the users whose favorite color is red. Clearly that's a cross-partition query. We need to visit every one in order to get the results. That query fans out, it gets parallelized, it gets aggregated, the results get handed to you. You don't have to do really any additional work, but clearly there's all that additional work happening behind the scenes, and that's obviously significantly more overhead than a single partition query, which is why you want to avoid these cross-partition queries. And then,
sorry, please do. Something I find kind of, I guess you could call it insidious in a way, is when you find yourself, or customers find themselves at a scenario where they're executing something like a cross-partition query that you have there and doing it with high concurrency. Like you said, it fans out to all the physical partitions. It can consume a lot of throughput, and it takes a long time. So higher latency and very inefficient usage of storage or of throughput. One of the first things I see customers do in reaction to that is they increase the throughput, because they think if I add more throughput, it's going to run faster. But guess what happens? The exact opposite. And you know why? because because now your query's got more physical partitions it has to traverse. It's consuming even more throughput and wasting all of that and taking even longer to actually execute. So it's a bit upside down in terms of how you deal with something like this.
Yeah, and it's not actually, and it's like you said, when it's high concurrency.
Yeah,
Right.
yeah. So, and that's right. And your point made, like you can't avoid these entirely, and applying kind of the Pareto principle to these, and applying kind of an 80-20 to this, but definitely for your high concurrency is where you should focus your
And
effort.
if you do have high concurrency reads where
Yeah.
you can't determine what the best partition key is for the vast majority of cases, because literally half the time it's one, half the time it's another, then that's a use case for a microservice that consumes the change feed of one container, replicates the data to another container, where the overhead of maintaining that replica is the cost savings of having that replica exceeds the cost of maintaining the replica.
Yeah, and you know what? It's people that come into this from the relational background. They're like, wait a minute, I'm wholesale copying an entire container.
Yeah,
That's
I know,
wasteful for
I know,
storage.
I know.
But you have to evaluate that against the cost of running.
You get a lot of wide eyes.
Yeah, and I've even told people, they're like, well, how many times can I do that? And I'm like, well, how many queries have you got, and how many of them are you running? Because you may make one copy, you could do two. I've seen customers use 3 or 4 copies of the same data and all serve different queries with different partition keys because they all run.
Remarkable.
Yeah, it's
So
yeah.
But we're here trying, in this data model, we're going to manage without replicating containers. But we'll do some denormalization in a bit. But clearly, we have to visit all of the physical partitions. So now let's pivot back. With that understanding, clearly, the most common queries are going to drive your choice of partition key. You need to ask yourself, you need to know if you can in advance. You can't always, like Mark was saying. But if you can anticipate what your most common query is going to be. For our customer-facing website, it's going to be that customer querying for their information, or maybe updating their information, which means it's going to be getting a customer, which means you're just going to need to know the customer ID, which means, in turn, that the ID property itself is the ideal choice for the partition key here. So now it's worth pausing for a moment and pointing out that a document is unique within a container based on a composite, a combination of this ID property and whichever property you choose as the partition key, which very often is some other property. But in this particular case where you're choosing the ID property itself as the partition key, it might seem like an odd pattern. It might seem even wrong, but it's not. It's actually, it satisfies my most common query, which is a point read operation where I just need to read and write one document at a time. Because embedded in each of these documents, don't forget, are all the addresses and the passwords. So anytime the user needs to retrieve their entire profile or change any part of their profile, it's a point read or write operation on that customer document, making the ID property itself suitable as the partition key, which also results, again, in what may look odd as a case where you only ever have a single document per logical partition. So certainly querying across customers won't be efficient, but within a customer, getting the addresses and the password, that's the partition key we'll go with. We'll go with that ID property. And I think it's about long overdue time for a demo where I'm going to do a quick query for customers.
Sure.
Right. So demo number 1 here, querying for customers. Here's a select statement where, I know the ID property of the customer, and normally, remember, that would not be, by the way, you might be wondering why it's a GUID if I got this data from Adventureworks, which of course uses integers. One of the things I did was I converted the integers into GUIDs, and I'll explain perhaps a little bit why later, but the point is that is essentially the primary key of a known customer, and I want to retrieve that customer by its ID. So when I execute that query, what comes back to me, hopefully if your demo wakes up, just went to sleep there a little bit, is the JSON document. There's the ID property, which is also our partition key. So because I'm using a GUID, it seems clear that it's globally unique, but generally speaking, when the ID property is not the partition key, this doesn't guarantee one unique document, because you could actually have two documents with the same ID with different partition keys technically. But we are partitioning on the ID, and the ID is a GUID. This gives us back the one and only document, which is the customer. But look, it also gives us back that array of customer addresses because we're embedding, and the embedded password. And the cost was 2.83 request units, which is about the cheapest cost of a query in Cosmos DB. Never going to cost less than that, but that's rock bottom cost there. But now I'm going to show you how I can, instead of running that SQL query, I can issue a read where if you know the ID and the partition key of the item, you can do a point read. And I'm retrieving a dynamic type, but it could also be a POCO. And when you do a point read, you just need to supply those two things, the ID and the partition key. And when those two things are the same, as they are in this case, because we're partitioning on the ID property, you just pass it in twice, the same value. That's the known customer ID, which is also, of course, the known partition key. And we get back what appears to be the identical document for Amanda Cook with the array of addresses and the embedded password at a cost of only 1 RU. So the point here, no pun intended, is always do a point read rather than a SQL query when you're retrieving one document and the ID and the partition key is known, where those two things are known, where if you're partitioned on the ID property, those two things are the same one thing, as we have in this case.
Yep.
Yeah. I actually also meant to flip on over to the Azure portal.
Oh, yeah, go ahead.
And show you that I have these 4 versions of our data model. That's the first one that we're discounting off the bat, because you can see it has 9 containers. And if I open up any one of them and look at the items inside, you'll see it's basically a JSON representation of what was a flat row in SQL Server with the additional Cosmos DB properties. But all of these this is just the columns of that row. There's no embedded addresses here. There's no embedded password. They're in separate containers. And each address is its own individual document, just like it was its own individual row in SQL Server. So, that's essentially a foreign key to the customer that owns this address, but there could also, of course, be other addresses scattered throughout this container. This is a very bad design, and we've graduated to WebStorm version 2, which you can see has far fewer containers, because I no longer have customer address or password because I've embedded them in customer, and I've also done other embedding. You'll see I don't have a sales order detail table as well, because, well, I'm jumping the gun here a little bit, a sales order detail container rather, because I'm embedding details within each order, right? So I'm reducing the number of containers and self-joining for performance, right? So moving on back to our discussion here. And let's try to ramp up the speed a little bit, because the next two are really simple anyway. They're just key value pairs. You still follow the same process. You take the table and you convert it to JSON. In this case, it's just a key value pair, ID and name. We're going to store, this is like metadata, right? Like our catalog. Our catalog of products, each product belongs to a category. So the category is metadata. There could be more than just the name, but we don't want to repeat the name or any other properties that might be unique to a category in every product that belongs to that category. Instead, we'll just carry the product ID, right? So let's think about our most common queries to determine the correct partition key. Well, the user is going to probably want to browse all of the categories, right? And then narrow things down by selecting a category of interest and looking at only the products in that category next. It's like a very logical flow. So we're going to want to get the whole list. This is a typical lookup list. This is not big data, but it's data that you need to store in your database. It's metadata. So if you think about your most common query, it's a select star with no where clause, right? Because you just want all the documents. And so the way we handle this in Cosmos DB is we just put the whole list inside of a logical partition. Logical partition is 20 gigabytes in size. None of these metadata lists, these basic lists of categories and tags, states and provinces, and things like that, like full lists, they'll all fit comfortably inside of a logical partition. So we want all those product categories inside one logical partition. The way we typically do that is by adding a synthetic property, if you will, for the purposes of partitioning, and we'll call it the type property, but every document will have the same value category, and we will partition on the type property, and by saying where type equal category, Cosmos DB knows exactly which logical partition to retrieve all the categories from. So you can retrieve all the categories and populate a dropdown or a sidebar or whatever it is, listing all the categories. So let's create some product categories. That's demo 2, querying for product categories. Right, there's this query we just saw on the slide. I'm querying from the product category container where type equal category. I'm getting the full list of categories. There's 37 of them. Like I said, they're just key value pairs. So you have the ID and the name. Every document, like I said, has a property of type, whose values category. So that's kind of meaningless data. And we also don't typically need those extra properties that Cosmos DB adds. So instead of saying select star, I'll just pull back the keys and the values. Here's something interesting to note. That query costs 3.85 RUs. This query that returns the same 37 documents costs slightly more, even though it's returning less data. It's ever so slightly. You're shaving hairs. It's like a fraction of RU. But it has to do with the overhead of actually processing the request for specific properties over using star. But that subtle detail aside, yeah, this is what I need. This is what I need to populate my dropdown. The user will see the names, and when they pick a name, I'll get the ID, right? So that's product categories. Product tags are very similar, keys and values. I don't have to rehash that. Same concept. Convert them into JSON documents, store them in a metadata container that, again, because we're going to most commonly want to get all the tags, perhaps, and then the user can browse by tag. We'll do the same thing. We'll lump them all in the same logical partition. We'll add a type property, but for these documents, we'll set the type to tag, right? And that's going to bundle all of them together in the same logical partition, and that works the same way. Products is where it gets more interesting. So for products, we've got one to many, right? And how do you handle that? I'm sorry, many to many, beg your pardon. For products, we have many to many with the tags table, right? And the way we do that in Cosmos DB is with a combination of embedding and referencing. You have two sides of a many-to-many relationship. On one side or the other, and choosing one or the other will depend on your usage patterns, but it will work if you do it on either side. On one side or the other, you embed references to the other side, right? So in this particular case, inside of each product, I have an array of tag IDs, and that way I get my many-to-many. Okay, I'm embedding references to my tags. How am I going to partition my products? Well, again, the most common usage pattern is the user will pick a product category first from our previous query, and then you're going to want to see all the products in that category. So it's most common query will be getting all products, querying on the category ID property by a user selected category ID. So that would mean that we would want all the products belonging to the same category to live in the same logical partition, which would mean choosing the category ID as the partition. So now when the user selects a particular category, I can get all the products in that category with a single logical partition query. But we have a slight problem here, and that is, given a product document in hand, do I have everything I need to display this product on my web page? Actually, I don't. I don't actually necessarily have the category name. I was just handed a category ID from which to select a bunch of products. But if I want to display these products, I don't have a category name to put at the top of the page. And for each product, there are also tag IDs. I don't have those tag names because those are in those metadata containers. Remember, product category is where I store the master data of each product category that I don't want to duplicate, like the name and potentially other properties. That's what I'm kind of linking by ID. So, but I at least need the name to display this product on my webpage and I don't have it in the product table, I would have to actually query the product category table. I would have to run 2 queries to get not just all of the products in a given category, but the name of the category as well. But much worse than that, I would then need to iterate each product returned by the first query and run this 3rd query to get the names of all the tags in that in the tag IDs array, right? Like getting all those values, I would have to generate a query like this to get the names in order to display this product in its entirety on my webpage. And if this all sounds painful and wrong, that's because it is. That's when relational developers like slam their fists down and say, where are my joins? Because of course, that's your answer in the relational world. And that's why we denormalize. And we do things very differently than we do in the relational world. We kind of throw away the value of normal form. And where in the relational world, we optimize for normal form. We optimize to avoid duplication. And we rely on joins and aggregations for on-demand processing. In the non-relational world, we'll denormalize. We'll favor fewer operations, even if it means wasting more disk space. Which again, of course, storage is cheap, right? It's not really about the storage anymore, but we still have to worry about data integrity when master data changes. That's really the issue. But what we're going to do again is like denormalize. We're going to duplicate. You see, I have got a category name here as well as a category ID, and that is a copy of the master category name. I'm going to have 10 products in the same category, and that category name is going to be repeated in all of them just to avoid the hop for an extra query. And the same with the tags. Instead of an array of string IDs, it is now an array of objects, where each object has not just the ID that we had before, but a copy of that name that lives in the master container, right? So if I have one of these documents in hand, I really have everything I need with this one read of this one product document to display this document on my webpage without the pain of those additional queries. So that means that at the point of insert, when these names are perhaps known, I make sure that I include them in a new document. But of course, the question then becomes, what happens if the master data changes? What happens if a category name changes? Where with the traditional join approach, of course, immediately all of the related rows, which would reflect that change. Here we have documents, and they're not really related. We've done duplication instead. How do we cope with this? It means anytime there's a change to a category name or a tag name, we want to propagate that to the product table. How are we going to do that? The change feed. Change feed is super powerful, and there's many different things it can be used for. And this is one of them. It is what its name makes it sound like. It is anytime you write or update a document to a container, that change is emitted through the change feed. You can listen in on the change feed. And in near real time respond. And it's also persisted, so you can always rewind and replay the events of the change feed if necessary. So it's a very powerful mechanism in Cosmos DB, and we're going to use it to help us out here with our data model for a little denormalization. And the easiest way to work with the change feed is with an Azure function, which wraps what's called the change feed processor library. But this is not a talk on change feed, so we're just going to think of it as an Azure function that has a trigger that wakes up anytime there's a change. In this case, anytime that master data changes, somebody changes a category name or a tag name in the master metadata container, our Azure function is going to wake up and update all of those copies, update all of the propagated copies of that master data, because each of those metadata containers has a change feed that we can listen on that will trigger an Azure function to wake up and propagate those changes. I'm going to show you right here on this slide all the code entailed. You've got a C# function with a function name attribute. That's what exposes this function as an Azure function. There's a Cosmos DB trigger that points to a particular database and container and connection string, and a so-called lease container for maintaining state. But this is all just kind of metadata. In terms of the actual parameters that are handed to your function, it's only these two, which are the only two that you need. A read-only list of documents that have changed. In this case, if somebody changes a a category name, you'll get one document. But in response to that one change, you may have to update many related product documents with change. And a logger for you to write output to. You will just iterate those documents, deserialize them, pluck out the ID and the name, and for each one, call update product category name, which is basically going to, this is going to iterate only once here if you only have one change. But that one change will, in turn, have an iterator that will find all the products in that category. Very simple, and it's a very efficient query as well, because it's a single partition query. So at once it gets all the products in the category where that duplicate data needs to be updated, and it retrieves them very efficiently in a single partition query and loops through them all. This line of code here changes the category name in memory, and this next line of code updates the document physically in the container.
I just want to point out that twice now we've pointed out how change feed is used, right? Like if you're building apps or designing or using data Cosmos, change feed is absolutely critical, I think, for pretty much anything you're doing, right? Like whether you need to serve queries from different partition keys or maintain referential integrity or just moving or copying data, change feed should be at the center of all of that, don't you think? Yeah.
Change feed is, I mean, it's really hard to think of any large scale scenarios that don't require change feed.
I had a question from a viewer here. How to work with dynamic schemas for .NET applications or object-oriented programming?
Yeah, that's a great question. Well, you know, we do have the dynamic type, which I actually showed in the demo earlier, this one here. Where I'm reading an item and I'm specifying dynamic, which means that I'm going to get back a dynamic type in C# that has, in a sense, essentially reflects the shape of the document as it's stored in the database. And I'm getting runtime property binding here. So I'm not getting any compile time checks. Everything will compile, but at runtime, if I reference a property that isn't there, I will get a runtime exception. I could instead define a class and reference that class here and have it immediately serialize into that property, into that type. I would need to know that via a where clause, or in this particular case, I know the type of document I'm retrieving with a point read, what type to expect, because if it doesn't fit, you'll get either properties that are dropped, you know, or vice versa in either direction. Yeah.
You know, this question comes up, and one of the things I recommend is like dynamic types are cool, but if you need to do something like versioning, where your schema is evolving over time, you can start with like a base type, right? That maybe has like and it's going to have ID, of course, and maybe a type and maybe a version, and then
you should always have a type and always have a version,
right? And then deserialize into that, inspect the property, and then depending on what the value is there, then deserialize into its proper.
Yes, if you don't know the type, if you got an array of unknown types.
Yeah,
indeed. Cool. So coming on back to our change feed demo here, I am going to run demo number 3, and here I'm going to retrieve 5 products from this known. This is a known category ID. This is the category ID for clothing shorts. I may have many documents, many product documents that are in this category, but I've only got one master document that has the name. So let me get 5 product documents, the top 5. You can see I've got a bunch of them. Here are the top 5, but they all have the same category name repeated: clothing shorts, and that's expected. But now what I'm going to do is I'm going to retrieve that master data document. Remember that we are partitioned on the type property, and that all of the documents have the partition key value of category, right? Because they're all on the same list, our product category list. So I know my ID of the product category. I retrieve it and I change the name from clothing shorts, to clothing fun shorts. And this line of code here replaces the item in the container. Now, before I run this, let me switch on over and make sure that my my Azure function is running, I actually have 3 of them. One for when the product category name changes, which is what I'm demonstrating now. We're changing the category name. And another for when the tag name changes. Remember, that's in a separate container. But in a later version of this data model, we're going to combine product categories and product tags into one container. So this third function here is actually for that more efficient version of the model, which handles changes to both category names and tag names. But we're not there yet. We're going to look at sync product category name. Here's a function that's currently running, and let's turn on the log. By heading over to monitor and log. I'm not sure why response is sluggish. It's like maybe my resources are being drained. I don't know.
Azure portal to the rescue again. Azure portal acting up again.
I don't know. This was just working moments ago. I think I'm hoping it's not my machine. There we go. I don't know what the logs. This is taking a little too long. Hopefully we don't have timing issues, but we should actually be able to see the function wake up in response now to this change. When I press any key to continue, it's going to apply that change. It says that I'm connected. I'm actually just going to wait another moment so we get another output. There we go. Okay, welcome. I'm now connected. All right, let's let it run. And it went ahead and made the change. Oh, there we go. You see this output in blue? That is output from my Azure function. I wrote to the console. That's where I ran I got one change document, and I retrieved all the products in that category, and I updated each one with the new category name, clothing fun shorts. When I go back to my client application and I run the same top 5 query we just ran before the update, you'll see that all of them have been updated to clothing fun shorts. I'm only showing the top 5, but in this case, all 7 were updated, or 70 if need, whatever the case may be, right? And there's denormalization at work for you. We're getting close because we're getting close to the end here. We are on our last set of tables that we need to bring into our data model, and I'm going to add yet a new twist here as we wrap it up here, because, well, again, beg your pardon. We start with step 1 by converting our column names into JSON property names so that it looks like a JSON document. And of course, the primary key is now simply called ID. And then asking ourselves embed or reference. And because we can comfortably fit all of the details of an order into a single 2 megabyte document, we'll keep the header with the details, certainly keep them all combined together, and then put them in a container, right? They're all of our embedded details. Put them in a container called sales order, right? And how are we going to partition on it? Again, that question gets answered by then asking, what are my most common queries? If I'm, again, back on a customer logged into the website, I'm going to want to see a list of all my sales orders. I will want to review all of my sales orders. So the most likely query would be, let's say, to get all the sales order for a customer. And there might also be another query that's, let's say, less common, a query that's, let's say, less common, that's not on the front-facing website where customers are, hundreds or thousands of customers are bombarding you with queries concurrently, but the occasional back office query where somebody wants to know who, some executive wants to run a query to get all of the best customers. They want descending by order count, so the best customers float to the top. Those are 2 types of queries. Let's take the first one. That's what the query looks like, right? To get all of the to get all of the sales orders, and that includes all of the details embedded within. For a given customer, it'll be select star from the sales order container where the customer ID is known. And that would mean that all of the orders belonging to a given customer will live in the same logical partition, and that's good. And that's what we want. And so that means we want to partition on the customer ID. But now is when you have to slam on the brakes and say, now hold on a second. This is not the first time. I mean, it might seem like a long time ago at this point. But it was only about less than an hour ago that we also chose to partition on the customer ID. It was the customer table. Remember, we partitioned on the ID property that has the customer ID. We partitioned on customer ID. And here again, we have decided to partition on customer ID. So we are questioning now whether we actually need that sales order table. Okay. Why is, what? Oops.
There you go.
It just kind of locked up on me.
Yeah.
Hold on. Let's try to fix this. I think it's back. Okay, I think it's back. It just kind of went fluky on me. But, you know, here, remember this customer table? It was partitioned on the ID property. This value here, that's the customer ID. We're getting exactly one document per logical partition, remember, because we were doing those point reads and writes at the customer levels, and that was appropriate. Here, we're also partitioning on the customer ID. Why do we need two separate containers? And the answer is that we don't. We can and I would say should combine different types in a container because we're schema free. There's no enforced schema. We can and should mix these different types, especially when, like we see in this case, they share similar access patterns and similar partitioning needs. Clearly, they share the same partitioning need to be partitioned on customer ID. Certainly appropriate to combine these two different types into a single container. Like not even have that sales order container. The customer container includes documents of both types. A customer, which itself has embedded addresses and an embedded password, as well as sales order documents that have embedded details. Both of those document types will live in the customer container. And that's and we have a little problem to solve here, which is that, you know, the ID property here is actually different. The ID property for a sales order is the sales order ID. And this is the quote unquote foreign key to the owning customer. Whereas the ID property in this case is the customer ID itself. And we need to pick one partition key that's the same in both. And the way we'll handle that is with a slight little bit of denormalization. We'll actually add a customer ID property here to the customer. Document where it'll be a copy of that ID property, right? So it'll still, you know, the ID property will still have the customer ID in it because we need to have an ID property, but a copy of it will be in the customer ID property, which is the same name as the customer ID property in this document. And then we can partition on the customer ID property, which they both share. So just a little bit of tweaking there. And we have to understand that the sales order document holds two copies of the customer ID in order to achieve this. But now it's a far better picture. And this is, by the way, what I told you I'd come back to it, why I converted those integers to GUIDs. Because a customer ID and a sales order ID, you know, so we'll have to be different, right? In this particular, the way I've combined them, okay? And they will be because I've gone with GUIDs. Okay, it's also a good idea to include a type property to be unambiguous about the type of documents that are being stored in the container, especially when you have different types. Like it's not required, but for your own sanity, I would strongly suggest always having a type property and really also always having a version property. So you don't have to make brittle assumptions. Like I can make an assumption here that if there's an email address property, then it's a customer because only customers have email address property and the sales order don't. But what if one day we add an email address property to the sales order, which can entirely possible. Think of all the code that will break on that horrible brittle assumption of that if. Instead, if if it's type is customer and type is sales order is definitive. Anyway, putting that aside, that means that we've got one document that's a customer and three documents that are a sales order in this particular case, all sharing the same logical partition. So if we want to get all the sales orders for a given customer, we can simply filter on customer ID and type. It'll be a single partition query and we'll get all their orders. Let's see a quick demo. Querying for sales orders. So look at this query. I know the customer ID, and I'm querying for sales order. I got them both. I got all the sales orders, including the sales order details. That one has only one detail, but this one's got several details. I got all of them for one customer, and very inexpensively, because it's a single partition query. And if I take the type portion out of the where clause and I include the customer, think about what I'm getting. I'm getting a customer. I'm getting now 3 documents. The first, and I've ordered by type, which is a bit of a cheat because the C in customer comes before the S in sales order. So that guarantees that the customer floats to the top. The customer document floats to the top, where I get all the customer information, all of the embedded one-to-many addresses, one-to-few addresses, the embedded password. I then get a sales order document and another sales order document. So basically all of the sales orders, and each one of those has all of the embedded details. Now, think about that, right? You're getting all your joins back. It's still a very inexpensive query because they are essentially either self-joined by being embedded or joined as in they're all in the same logical partition. So they're kind of joined that way. And you have an extremely efficient result here, retrieving all 3 documents with the customer, their addresses, password, all of their orders, and all of their embedded details for just 2.89 RUs. It's only 3 documents, and if it's many more documents, the cost will go up, but it will be the cheapest possible query in Cosmos DB for this.
I got some questions. Wonder if I know you got one more thing to show here. Can we do a couple questions?
Sure.
All right. Just going back to change speed, what's the incremental cost if you work with this log with Azure Functions? I don't know what that means. Like Azure Functions won't cost any more to run if you use the log.
Azure Functions, yeah, well, there's a consumption-based model that is free, right? And then there's a provision model where you pay for dedicated.
Right, and it keeps and it keeps the instance hot the whole time.
Correct.
Yeah.
Like I cheated before I gave my demo while you were talking there, Mark. I stopped and started the service because it has a tendency to go cold even while you're in the middle of giving a presentation for that reason. But you can, because you're not paying for it, essentially. Right?
That's why I always use premium.
But you can pay for it. By the way, you can also host it yourself without using an Azure function.
Yeah.
You can host the CFP, which is what most people do.
You could fire up an AKS cluster and host it in there, even if you wanted.
You can, but I would be the guy to turn to for that. You'll find someone else, some container person who can figure that out.
Another question: why use change feeds instead of just inserting the logic directly in the rename function, for example?
Well, because you're gonna want that kind of like trigger behavior. You're gonna want to know that no matter where the change comes from, it gets fired. And you might think of actually using a trigger in Cosmos DB because there are things called triggers, but they actually won't work.
I mean, this is more of an architectural question, right? It's a separation of concerns. Like I should not have to refactor my code if I add something downstream that cares about the change category.
You will have to be sure that your developers, every time they make a change to the category name, they invoke this logic as opposed to just knowing
subscribe to the event, basically. Capture it that way. So let's see. When generating customer ID in the app logic or auto-generate by Cosmos. I can answer that one. You should generate the IDs yourself. Our SDK used to generate it, but
yeah, Cosmos never generates it the way the question is phrased.
Not anymore.
If you go into the portal and you create a document and you don't supply an ID, you'll see a GUID gets generated, but it's the portal that's generating that GUID. So you have to generate that GUID, whether you. This is another loaded question because the question is really, are GUIDs a good choice? And they're often not a good choice, but often they are. And but in most cases, it's better to come up with something a bit more meaningful. That's a composite of other properties, perhaps, with something to make it unique. Yeah.
But there's no, by the way, there's no auto increment in Cosmos.
That as well. Yeah. There's no.
Using straight integers is generally not a good idea, especially if you're relying on something like an auto increment. You'd have to roll your own integer dishing service, and that's
it's best to either construe one that I mean, it's guaranteed at least to be unique within the partition key, but that's dangerous because then you can't easily, you make it harder to change the partition key if you have to later and rebalance things. But, it has to at least be unique within that partition key for the partition at the time.
Yeah, exactly.
Yeah.
And plus, if you're going to do inserts, like say on a transaction or something, and you need combined values there, you need to pre-generate. You can't wait.
Yeah, even if ultimately you can always generate a GUID.
Yeah, right. Okay, a couple more, and then we'll get back. The field type is for separate documents or for queries?
We were using it for both. We were using it as a partition key. So let me answer that question visually by heading back on over to the portal and going to our now web store v3 it looks like it has an extra container, but it doesn't. This lease container is not part of our data model. But inside of here, if I open up any product,
I don't think there's a type property on product, is there?
No, there isn't, but you will see that in addition to the category ID, there's the category name. In addition to the tag ID, there's the tag name, right? This is the duplicate data that gets updated by the microservice. The master data lives inside the product category container, which these are all of the categories. There's not that many. This is our entire list. So they all fit inside one logical partition. The partition key is the type property, and they all have the same value.
Yeah. The way to think about this is type defines an entity. Is the way I kind of refer to it, because you can store different entities in the same containers, provided they share the same partition key, and you need a way to disambiguate that. So you need to define what type am I looking at here.
Well, and actually, in our particular case, it's like you really want to do a select star without a where clause. Because you want all the documents in the container. In this case, because you're not mixing types, which is
for that
matter. But that would be a cross-partition query without a where clause where you specify the partition key. It's going to be cross-partition. So we just add the type property to everyone. So the answer to your question is that it's used for both, for partitioning and for the query, right?
Yep.
To make it a single partition query. Hey, we're getting close to being wrapped up, but remember we had one more type of query. That back office query, right? To get my customers by descending order count, so the best customers float to the top. Now, in the relational world, this is just yet another example where it would be a no-brainer, where you would have a join and do a select count, and you would just the aggregation would just happen on the fly. But in this world, we can't, right? That doesn't exist. So we need a better way to achieve this, and we'll do that by actually more denormalization. We'll actually store as a new property inside the customer document the sales order count. So whatever that number is, that's how many orders that customer has. And so that number needs to go up each time they place an order. And then the query becomes very simple, right? As you'll see in a moment. But that does mean that if customer A creates a new sales order, we need to update the customer document as well and change it from a 3 to a 4. Now there are 4 sales orders. Right, we need to change that 3 to a 4. And how can we do that? And if you're thinking change feed, you could be on the right track. You could use change feed for this, but actually in this case, because we're dealing within a single logical partition in every case, it's actually better to use a stored procedure. This is going to be JavaScript, and just to give you a heads up, but this can also be done in C#, so don't fret. There's a transactional batch feature that works conceptually the same way, because Cosmos DB can transactionalize the updates within a logical partition. This is what the JavaScript looks like. So when I need to create a new sales order, rather than adding it directly to the container, I'm going to call a stored procedure and pass it in as a parameter, and let the stored procedure not only add the document, but also update the customer to increment the count. This just gets a bunch of variables to prepare for what is a bunch of nested callbacks. But the gist of it is the stored procedure retrieves the customer document, increments the sales order count, and that happens in memory. But then when it calls replace document, it writes that change to the container. But because we're inside of a stored procedure, it's transactionalized, meaning it will not be committed if an error occurs. So after that document gets replaced, with the incremented sales order count, then we can actually create the new sales order document by adding it to the container. And only if the store procedure completes successfully will both operations, this replacement and this creation, commit, or they will both roll back. You'll never have a sales order count that's out of sync. And then the query becomes really simple. Like I said, just order by sales order count descending, knowing that that number is a reliable representation of how many order documents there actually are. This will be our last and final demo. So let's query for our top customers. If I flip back on over to the portal and look at our final version of the data model, we see we're down to 3. Again, the lease container is not part of our data model. It's used by the change feed. We brought everything down to customer and product, because now the customer container also has sales order documents in it, right? Remember, because they're all partitioned on customer ID. Products has products in it, and product metadata is I've combined categories and tags because they are both partitioned on the type property, so they don't need separate containers, right? So I really brought this down, and inside of the customer container, if you look at stored procedures, you'll see there's that stored procedure we just saw on the slide. There it is. It's just sitting there, and we're going to call it now, right? So let's do that. We're going to do demo number 5, our last and final demo. We're going to run that query, that top up. Now remember, now if you look at this query, this is a cross-partition query, but it's not evil because it's not a typical query being generated by our customer-facing website on the front end. This is just an occasional query that we run on the back end just to get our top customers, because obviously we have to run this as a cross-partition query across the entire container to get the top 5 customers. You never know which logical partition the top 5 are going to be in, right? So it's a cross-partition query, but it's perfectly fine. I'm going to go ahead and run it, and you can see Mason Roberts and Dalton Perez are both tied for best customer at 28, and then after them comes Daniel Davis with 27, and so on. So what I want to do now is I want to create a new order for Dalton to push Dalton up as my top customer with 29 orders. And how am I going to do that? This is my C# code where I'm going to, and to the several questions that came up earlier, I'm using a dynamic type, but it doesn't have to be. It could be a POCO class, right? It could be a strongly typed class. In which case, these could even be Pascal cased properties that get converted automatically to camel case on the back end by using the JSON property attribute in your class definition. Furthermore, I'm generating the GUID. I'm generating the ID as a GUID, but we discussed about how you might want to come up with a better value, but either way, you have to supply it. It will not be supplied by Cosmos. And there's my customer ID. This is the customer for this order. This is the customer that has placed an order with these details. Rather than taking this document and writing it to the container directly, I'm going to execute a stored procedure. And this is the type returned by the stored procedure, actually, which is not really relevant in this case because we're not returning anything meaningful. We just want to make sure that this operation is transactionalized. The name of the stored procedure, the partition key, which is, of course, the customer ID, because that is the scope of the transaction. All changes made within that customer. So anything about that customer that you change is going to be transactionalized. And the parameter array, only one parameter, which is the new order that we passed to the stored procedure. We call the stored procedure. It costs a healthy 22 RUs. And now let me run the same top 5 query as we ran before. Now you'll see that this time Dalton Perez has surpassed Mason Roberts with a sales order count of 29, making Dalton our top customer. And there you have it. So that brings us to the conclusion. Yeah. Thank you. To wrap it up, our final design is we've got one customer container partitioned on customer ID. There's 2 document types, each of which has embedded data for very efficient access to customer information. A product container with our products in it, And we had a product tag container and a product category container for our metadata, but they're both partitioned on type. Just in one case, the type value is tag, and in the other case, it's category, but there's no reason for them to be in separate containers. So our final design has combined them into one, partitioned on type. Now, it's been a long session, and I'm basically done here, but I don't want to blow your mind here, but there's actually a way that you could bring this down to one container if you wanted. And there are people who do that. I know people who do that. And it could be argued that it becomes overkill at a certain point. You can go overboard and over-engineer this thing. But technically, you could have one container whose partition key is PK, whatever value you store there. You store, in the case of a customer or a sales order, you would store a copy of the customer ID in that property. In the case of a product, you would store the category ID in that PK property, and really just kind of mush everything together. But it's when your partitioning needs are the same, that's when it's best to combine multiple types into one container, like we did for customer.
Plus the access patterns as well are going to be a problem.
Access patterns are different.
Yeah.
You might want to raise or lower throughput on customers independently from products. So I don't think it would be a good idea to mush this all together, even though technically you could. And so the key takeaways here: you want to identify those key access patterns, and knowing your most common queries, that will enable you to design for them. A clear understanding of partitioning is critical to achieve that scalability and performance. Two different ways that you can materialize those relationships are by embedding or by denormalizing and or pre-aggregating, like we saw in a case for the sales order count, and also making sure that related entities are stored in the same container and ideally in the same logical partition as well. You can denormalize either by using the change feed or by using stored procedures or by using the actually transactional batch. Thank you. Sorry if we went a little bit over than what you might have expected.
That's okay. I don't think we lost any viewers, actually.
We're about 75 minutes there. I think we started about 5:15.
Yeah.
So,
well, thank you very much, Lenny. This was great. I know, this is such a, like I said at the beginning of the show, this is such a critical topic.
Yeah. It never gets tired.
What's that?
It never gets tired.
No, I mean, these are all things that every time you work with Cosmos and design a new workload, you've got to face and deal with these things, and understanding these concepts around understanding access patterns. How are people going to use your app? Understanding the entities that are used within them. All these things matter. And in some cases, sometimes Cosmos forces you to think about things a little more deeply at a very early stage than maybe you would otherwise have to in like a relational design. But entities matter, patterns matter, all those things matter. So,
and everything I covered applies if you were using the MongoDB API, because from a data modeling perspective and from a partitioning perspective, the concept is identical, right? Whether MongoDB or SQL API.
Yeah. So
of course, SQL queries, but
yeah. All right. Well, just no more questions. But hey, Lenny, thank you so much. It's always great having you on the show. We'll get you back. We'll talk about. We should talk about microservices.
Sure. Pick a date.
What's that?
Pick a date.
Okay. Okay. We'll
pick a date. I'll be around.
All right. Great. Well, thank you everyone for joining us this week. Really hope you liked our episode. Next week, we're going to talk about something kind of different and new, the new Azure Developer CLI. This is a brand new way to be able to basically manage and deploy resources up in Azure. So we're going to talk.
You know what we need? A new way of doing the same old thing. Sorry.
I suppose.
Sorry.
I play with this developer CLI. I think it's pretty cool. So
I just let that slip out.
No, that's okay, Lenny. We love you. We love you
too. Thank you.
Yeah. Hey, folks. Thank you so much, and we'll see you next week. Take care, everyone. Bye-bye.
Take care.